Hello and welcome to this session of ACS Science Talks, connecting the world through science. This is the virtual lecture series, Scientific Talks by a specialist on specialized topics for a specialized audience. I'm Kunal Gupta, and I'm pleased to be your host for today's broadcast of ACS Science Talks. Now, before we begin the session, it is my pleasure to invite Dr. Diksha Gupta, a Director of Global Strategy for Society Programs at American Chemical Society, for an opening remark. Diksha, over to you.
Thank you, Kunal. I'm pleased to welcome all of you to this broadcast of ACS Science Talks, a platform by ACS to connect the global scientific community. As the Director of Global Strategy for Society Programs at ACS, I'm honored to interact with you today and share our global outlook and mission to support all science professionals. At ACS, we are dedicated to provide the necessary resources for students, scientists, academicians, industry professionals, and broader scientific community to thrive in the dynamic world. Our focus is on fostering innovation and effectiveness in scientific education. We provide access to opportunities, resources, skills training, and networks, ensuring that you have the support you need to excel in your endeavors. By doing so, we contribute to the growth and success of the global scientific enterprise. We believe that diversity, equity, inclusion, and respect are fundamental values that drive progress. We are committed to promoting these principles as we work to identify and dismantle barriers to success. Our aim is to create a welcoming and supportive environment for all individuals, regardless of their background or circumstances. Together, we have the power to bring a positive change. Through collaboration, knowledge sharing, and the application of scientific expertise, we can address the most pressing challenges being faced by humanity. By supporting science professionals like yourselves, we are laying the foundation for a brighter and more sustainable future. I'm grateful to each and every one of you for your dedication to the scientific enterprise. Your work is essential, and it's our privilege to stand alongside you in this remarkable journey. Thank you, and I'm sure you will have a great time listening, Professor Wang. Over to you, Kunal.
Thank you, Diksha. Our speaker for today is Professor Peng Wang. Dr. Peng Wang is a faculty member at the Hong Kong Polytechnic University. He joined King Abdullah University of Science and Technology in Saudi Arabia in 2009 as a founding faculty member. He was the chair of Environmental Science and Engineering program at KAUST from 2013 to 2017. His research focuses on renewable energy-driven clean water production and wastewater treatment and sustainable water energy nexus. Dr. Wang is a fellow of the Royal Society of Chemistry and an ACS member for 12 years. He was awarded the Mohammed bin Rashid Global Water Award in the category of Distinguished Researcher in 2023. And he was also awarded the Xin Guanxing Distinguished Alumni Award of Nanjing University, and please pardon my pronunciation of that award name, in 2021. Ninth Prince Sultan bin Abdulaziz International Prize for Water in 2020, and NANOVA Frontier Research Award from the Chinese American professors in environmental engineering and science in 2020. Dr. Wang serves as an executive editor and associate editor of Environmental Science and Technology, an academic journal published by American Chemical Society since 1967. He's a member of the advisory committee on water supplies at Hong Kong. Thank you, Professor Wang, for joining us. The stage is yours.
Thank you, Kunal, for a very nice introduction. I would also like to thank our wonderful ACS India team for initiating such a wonderful, impactful platform. It is my really great pleasure to be part of the ACS Science Talk. So today, I want to share my research activity progress in the past 4 or 5 years on renewable energy-driven decentralized clean water production from unconventional sources. So as you can tell, in this talk, I'll try my best to convince you that this research topic is important. And also we'll report some of our progress in the past 5 years to you. To start, I want to say that everybody needs fresh water. However, our future of fresh water supply is not so promising. As you can see from this slide, by 2040, more than 80% of the global population will have high chance of experiencing freshwater scarcity of different degree. That includes the entire region of India and China. Now, that's a future. What about now? Well, there's a very grim fact that says that at this point, there's still more than 800 million people in the world who still do not have direct access to clean water. Now, this is the reason why we have 17 sustainable development goals set by United Nations for us to achieve by 2030. Out of those 70 SDGs, I want to focus on SDG 6 and SDG 7. Now, 6 says clean water and sanitation for everyone. Now, 7 says affordable and clean energy for everyone. Now, think about how can we achieve those goals by 2030, right? Obviously, connecting the impoverished community into energy, into water grids is either not possible or very expensive. Now, I always think that development of decentralized drinking water production, decentralized energy supply system is the best way for us to achieve at least SDG 6 and SDG 7 by 2030. We have 5 major categories of renewable energy. Now, out of those 5, solar energy has the highest abundance. Now, out of all of the solar energy utilization of purchases, photovoltaics or PV is the most popular one at this point. Now, on our way of achieving our ultimate sustainability, our carbon neutrality, we have to utilize solar energy as much as possible. Now, for a sustainable solar energy and the water nexus, there are 2 aspects. Now, the first one is that we have to use solar energy to help us to produce water, to produce as much fresh water as possible. Now, the second aspect is that if we can utilize water, especially water from unconventional sources, to help solar energy to give us more electricity. Now, if we can achieve both within the same picture, we can move faster on our way of our solar, of our carbon neutrality, of our ultimate sustainability. Now, this is very general background of my talk. Within next 30-35 minutes, I'll be talking about 3 research directions. The first one is solar distillation. Now, the second one is atmospheric water harvesting. The third one is solar crystallizer for brine treatment. Now, get into the first topic, solar distillation-based clean water production. Now, you may or may not know that the first ever solar steel in the world was invented 500 years ago in the Middle East region by Arab alchemists. Now, the conventional solar steel has this general structure as I presented on the far left side. Now, the general structure of solar steel has not been significantly modified or changed in the past 500 years. Now, from modern science point of view, excuse me, there are 2 major drawbacks of conventional solar steel design. Now, the first one is that such a system has low evaporation rate. Now, the second drawback is that the system has a low vapor condensation rate. Now, if a system has those two drawbacks together, now such a conventional solid steel cannot produce fresh water at a high rate. Now, based on the conventional solid steel design, the ceiling for such a system to produce fresh water is no more than 0.5 liters of fresh water produced out of each square meter of solar irradiation area per hour, or 0.5 LMH. All right, LMH is the unit I'll be using, very often throughout of today's talk. Now, the reason I bring out this conventional solid steel was that the conventional design has been revolutionized in the past 6 years. I'll talk about this in the first part of this talk. Now, if you look at the energy pathways of such a system, all right, you see, once you have the heat being produced, now the heat will have multiple channels. The heat can be lost by conduction, can be lost by convection. It can be lost by thermal radiation or radiation loss. Now, those three is considered as energy loss. Now, for solid steel to produce fresh water with high energy efficiency, we need the energy to go to evaporation side. Therefore, for an effective solid steel design, now we do our best to minimize the energy that goes to those non-evaporation pathways. All right, so this serves as guideline for the solar steel design in the past 5 years. Now, I did not forget about how heat is produced. Well, the heat is produced by photothermal material. Now, that's a reason our group and many of our research fellows in this region in the past 5-6 years work on multiple photothermal materials. You can see here their polymers, their plasmonic materials, mixed metal oxide, MXene, and the one that is being shown here is, if you can follow my mouse, is a carbon photothermal cloth that we developed. Now this one is a photothermal disc that has a very high mechanical strength. Now, one very obvious question now is, which one of those photothermal material is the best? That was a question we had for ourselves. In order to get the answer to this question, we developed a very unique photothermal conversion efficiency measurement system. For the sake of time, I'm just gonna skip the detail and just tell you the results that we got from our measurement system. Now, in this table on the right-hand side, I compared two material. The top one is a very fancy material called MXene. Now, the bottom one is a very common carbon-based material, carbon nanotube. Now, the results may be surprising or maybe not surprising for you. The results says that those two materials both have very high photothermal conversion efficiency. Both are close to 100%. So the conclusion we get from this measurement system is that, well, very expensive, fancy material is not necessarily better than those common, conventional, cheap material. All right, what implication does this results tell us? I'll leave that to you. Now, guided by the energy analysis I presented in the previous slide, this field of solar to vapor conversion has progressed very significantly very fast in the past 6-7 years. You can see here in 2014, the energy efficiency was only 25% with the conventional design. Then there was the interfacial heating design that boosted the energy efficiency to 56%. When there's the Photothermal insulation design, 73%. And then when you separate the insulating material with the water channel, you got 87%. Now for me, the most exciting part in the field happened in 2018, when there were a couple of very nice three-dimensional evaporator design were reported. I used one of our work to demonstrate why this three-dimensional structure is very significant. Now, if you can utilize solar energy to its full potential, 100%, all right, your water evaporation efficiency will be at 1.5. That's a maximum. That's a ceiling. Now take a look at this red curve here. You see, in our system, we could achieve evaporation rate that was much higher than 1.5, as high as 2.1. What was the reason? Two reasons. They were listed on the right-hand side. The first reason is that such a design was able to harvest, to convert solar energy with very high energy efficiency, almost 100% to heat. Now, the second reason why such a system can break the ceiling was because with this design, as you can see from this top part of the design, during water evaporation, the majority part of the evaporation surface has a temperature that is lower than the ambient air. Now, there is favorable temperature gradient that drive energy to come from the air onto the material. So such a design has two energy sources, solar energy and ambient air. So that explains why our system was able to break 1.5 this ceiling. All right, I'm gonna leave this topic and move back to PV. Now, PV is not without any issue. As a matter of fact, PV has a solar to electricity conversion efficiency between 10 to 20%. So this means that 80 to 90% of the harvested solar energy is converted on PV panel into heat. This is the reason why PV panel can be very hot during daytime. By prediction, by 2030, the total amount of the waste heat generated by all of the PV panels in the world will be more than the electricity generated by the top 3 producers, India, China, and the United States. So if we can do something that can help to turn the waste heat of the PV panel to do something useful, that would be great, right? So in 2019, we designed and reported this photovoltaic-membrane distillation design. The conceptual design is presented here. Let me walk you through this design very quickly. So we have the membrane distillation system on the backside of the PV panel. As you can see, during daytime, when the waste heat is produced, and then the heat will be utilized to drive water evaporation. And the water vapor is generated. The vapor will go through the MD membrane and then be condensed on the other side of the first stage of membrane distillation. Now, the design of our system was able to connect the vapor condensation latent heat and utilize that heat to drive the second cycle of water evaporation. So this cycle can go on and on. Now, as you can tell from this conceptual design, this design should be able to produce fresh water at very high rate. All right, that's right. If you can take a look at water production curve on the top right, our water production rate was higher than 1.5. In many cases, close to 2.0. All right, this is very high, and the produced water is very clean. And the photo on the top left was our first generation design prototype. You may say this is really ugly, but for us, this design is breathtaking. Why? Well, this is solid steel, and you don't see any part of this device that is transparent. Now, this is unthinkable or imaginable before we reported this work. That's why I said this is significant progress in the field. Now, many readers agree with us. That's why our paper reporting this design got a lot of attention. So so far I had 66,000 the downloads. Now, for our latest generation of the PVMD, you can see the device was able to produce fresh water at this rate, 4.0. All right, we almost double the water production rate from the first generation, but that's not what I want to emphasize. What I want to emphasize here is this figure in the middle, in the top middle. And you can see here, now, while producing fresh water at this very high rate, now the water production unit on the backside of the PV panel was able to cool down the PV panel significant by, as you can tell here, by almost 15 degrees Celsius. Now, PV panel is cool. Therefore, the same PV panel will be able to produce more electricity while producing fresh water at this high water production rate. In our case, the same PV panel was able to give us 11% more electricity than the same panel without this water production unit. That's why the editor-in-chief of Joule invited Professor Hall from NUS to write a preview to highlight our this very interesting design for the PVMD. Now, the latest generation of the device looks, I wouldn't say much prettier than the previous one, because as you can see here, at this point, we are able to make this device very thin, and that can be not close to the commercial size of PV panel, but at least at this point, 1/4 of the commercial size of the PV panel. Remember, such a system is able to produce drinking water without consuming any electricity produced by the PV panel. And in contrary, it was able to help the PV panel to produce electricity, more electricity. All right, to end this section, I want to very quickly show you guys a project we did 2 years ago. Now, this project reported the first ever flexible MD design. Now, the reason why we make this flexible was that we want you to use this device while you are on the go. When you are traveling, you can put this device in your bag. When you need water, all right, you can put it outside on the top, on the roof of your car, on the outside of your school bag. All right, so this is the first topic. Now, the second topic is on the atmospheric water harvesting. There are really a lot of water in our air. Now, the total amount of water that is in our air is constantly 6 times of all of the river we have in all of the water we have in all of the rivers on Earth. Therefore, so long as we can figure out a low carbon method to harvest this very precious water out of air to produce fresh water for us, it would be great. Now, our approach is sorption-based. Now, for this approach to work, you have to have a specially designed sorbent. Now, the sorbent, when you put it outside, should be able to harvest or to sorb water vapor from the air. Now, when the sorbent is saturated with absorbed water, then you take this and put it in a closed or semi-closed chamber, all right, in the presence of some low-grade heat, like solar energy produced heat, low-grade industrial heat. Now the water will be evaporated out. Since this evaporation happens within a closed chamber, then the water vapor condensation will produce fresh water for you. This is how this system works. Now you see the key or the essential part of such a process should be the sorbent itself. All right. It is for this reason our group worked with multiple types of atmospheric water harvesting sorbents. We work with salts. We utilize the hydration reaction of the salt to harvest vapor from very dry air. Then we move to deliquescent salt in hydrogel. As you can see, those are the real photo of our hydrogel that can harvest water from dry air. We also utilize some nano design to enhance the vapor sorption kinetics, vapor desorption kinetics. We even produce a continuous AWH design that can continuously harvest water vapor and continuously produce fresh liquid water. Now, to convince you that such research is important, I encourage you to imagine that you are hiking alone in a very remote desert. There's no any visible fresh water source in your sight. What do? I don't think you can do anything in that very extreme circumstances. However, if you have some of our atmospheric water harvesting material and a very simple system, without any electricity being consumed, you can get some very precious drinking water from very dry and very thin air. I hope you guys can now believe such a research is important. Now, we also work on producing metal and chloride-free sorbent. The reason we need such type of sorbent is that in conventional atmospheric water harvesting sorbent, right, there's typically chloride. Chloride is very corrosive to metal. As you can see here, when you have chloride, this aluminum plate gets corroded very quickly. Now with our all polymeric sorbent, you don't see any corrosion phenomena even after 6 months. And last year, we realized that this well-known salting-in effect, if properly utilized in hydrogel-based sorbent, can enhance atmospheric water harvesting efficiency and can help us to produce more fresh water from dry air. And in our case, we design polymers with the both the positive and negative charges within the same backbone of the polymer. In that case, we call the polymer as the beta ionic polymer, all right? So we reported this work last year. Somebody who are in the field may argue and saying that, oh, you are not the first one to report this design. Professor Yu at UT Austin was. Now, in our defense, all right, as you guys can see from this comparison here, we believe our group and Professor Yu's group both reported the same principle pretty much at the same time independently, all right? What can I say? I want to say, this is interesting research area, and we are happy to be in the competition. Now, besides giving us fresh water, what else can the water vapor in the air offer us? Cooling. How can we do that? Well, the design is very simple. Take a look at this figure A here. That was exactly the same material as we used in one of our previous water production experiments. So we took the same material, we stuck this on the backside of the PV panel. Well, guess what will happen? Now, what happened is what I presented in this figure C. You see, with this hydrogel on the backside of the PV panel, the temperature of the panel can be reduced by more than 15 degrees Celsius as compared to the one without this hydrogel. Now, what happened? Well, it's actually very simple, all right? So this material absorbs water vapor from air. During daytime, when the panel is heated up, the heat will be transferred from panel to this hydrogel on the backside. Now the heat drives water to evaporate out of the sorbent. Now, water evaporation is a phase change process that will take a lot of heat. It's like our human body sweating, but this is how we keep our body temperature stable. In our case, we use the hydrogel sweating to reduce the temperature of the PV panel. With this design, we reduce the temperature of the PV panel, and therefore we were able in our test to increase the electricity production rate by 19%. All right, this is very significant energy enhancement. All right, now for the PV panel that could be cooled by hydrogel, remember the cooling process involved the evaporation of the absorbed water vapor. All right, what if we actually connect this water vapor? Then we will have fresh water produced, right? Now this photo here show you, our pilot scale testing with those three PV panel give us fresh water here. All right, we did this experiment in Saudi Arabia. The temperature was very high. The atmosphere was kind of dry, but with this water produced, we were thinking we could do a little bit more than cooling, more than fresh water production. What did we do? We used the water to grow crops. In our case, those 32 water spinaches were fully watered by the water produced by those PV panel. Remember, those PV panel produce water from nowhere, right? There was no any liquid water source. Now, that's the end of second topic. So I have about 7-8 minutes. That should be enough for us to go through the last topic of solar crystallizer for brine treatment with zero liquid discharge. Now, there are many chemical processes, industrial processes that produce highly concentrated brine. Now, one of this industry is water desalination. In Saudi Arabia, more than 80% of the drinking water is produced by seawater desalination. Now, seawater desalination of any kind, while producing fresh water, produce significant amount of brine. At this point, all major seawater desalination plants discharge brine without any treatment. directly back to the ocean. All right. Now the discharge brine contains the chemicals, contains the disinfectant, contains anti-scalant that were added during water desalination process. So discharge without any treatment of desalination brine directly back to the ocean has significant environmental concern because it harms the marine ecosystem. Now, the best way is always to treat those brines towards zero liquid discharge. Now, technology is available to do so, but it is either very expensive, as I show here on the right-hand side, or the energy efficiency is not so high on the right-hand side. Now, we believe solar crystallizer is a very good choice for brine treatment with zero liquid discharge. So before 2018, people use conventional two-dimensional flat, flat sheet type of solar crystallizer to treat brine. Now, this is a good design, but as you can see here, with this design, you have continuous accumulation of the crystallized salt on the surface of the photothermal material. So the process itself cannot be continuous because you have to keep removing the accumulated salt so the next cycle of the operation can start. Therefore, we were thinking, how can we make such a solar crystallizer to be continuous? All right, our idea was to produce three-dimensional solar crystallizer, as I present here. Now, we think this design might work because when the brine is being delivered to the center of the bottom of this three-dimensional structure, it will spread out, move towards the side, and then upward along the wall. All right. Now, with this design, the evaporation takes place only on the external surface of the wall. Therefore, there will be no salt accumulation in the inside of the cup. All right. Therefore, we separate, by this design, we physically separate the light absorption area from the salt accumulation area. Will this design work? Let me show you what really happened in our experiment. The news is this: the design works, but partially. All right. Please follow my mouse along those red dots here. Now we made three-dimensional structure according to our design, and we tested the performance of the design with 24%. This is % of pure sodium chloride solution. The system worked perfectly. And you can see, we have very stable, continuous evaporation rate. And you can see from the photo in the middle, in the middle part here, we have beautiful spherical aggregates of the sodium chloride. It was great. However, when we switch the test solution from the pure sodium chloride solution to real seawater, guess what happened? What happened was very disappointing because you can see here with those real seawater brine, real seawater, concentrated seawater, by the end of 20 hours, the system break down. Well, the system completely failed because there was no evaporation at all by the end of the first 20 hours. What happened? Right? What happened was this. As you can tell from this real seawater surface salt crust, there was very tight salt crust formed on the surface of evaporator. And with this very tightly packed crust, there was no space for water to transfer. Therefore, the evaporation stopped. Now, in order to figure out a solution to this issue, all right, we took a lot of SEM images to analyze, to hypothesize what happened. All right, at this point, what we believe happened, or our hypothesis is this. I want to stress this. Our hypothesis might not be right one, but our hypothesis led us to find a solution for this issue. So our hypothesis was this, right? Because this is the seawater, sodium chloride is a major component, all right? We believe sodium chloride crystallized first. When it does so, it forms this porous aggregate with a porosity around 19%. Now, the troublemaker in the real seawater is magnesium sulfate. And magnesium sulfate crystallizes at a later stage. When it does so, it occupies all of the pores previously formed by those sodium chloride aggregates. So by the end of the crystallization, magnesium sulfate blocks all of the pores of the sodium chloride crystals. So without any pores, there's no water transportation channel. Therefore, there's no evaporation at all. The whole system breaks down at that point. Now, that's our hypothesis. Based on this hypothesis, we also have a theory, right? If we are fortunate enough to find a chemical, when added to the raw brine of the real seawater, this chemical can selectively change or enlarge the porosity of sodium chloride. All right, let's say it enhances the porosity from 19.3% to 50%. Then the troublemaker, magnesium sulfate, will not change, will not block all of the pores. So therefore, when you have such a chemical, then you should be able to solve this very tightly packed cross formation issue. All right, I would say that we were really lucky to find a chemical called NTA, not very expensive, it's even biodegradable. So we took this chemical, add just a little bit into, in this case, into the pure sodium chloride solution. We want to see whether this chemical can enhance the porosity of the sodium chloride crystals during the evaporation crystallization process. Now, pay attention to this figure B at the the bottom right. See, the same amount of the sodium chloride solution with the same concentration, with different amount of NTA being added. You see, without any NTA, this solution produces this amount of the salts. All right, the bulk volume is this much. With a little bit of the NTA being added, you see at a certain point, you enhance the bulk volume from this little to this much. So this chemical can really enhance or selectively enhance the porosity of the sodium chloride. Then we did our experiments with the real seawater. The same thing happened. We are very happy because as you can see here, with the chemical being added to the real seawater brine, we have very fluffy, solid form on the surface of our solar crystallizer. Now, the bottom right video is kind of a specially processed one. just to show you, we don't have with this design any, salt crust formation issue. We can have with this chemical a very nicely continuous process of seawater brine treatment. Now, to end this part, I have this vision in my mind for a very long time for brine treatment with zero liquid discharge. So I believe any industrial brine can be treated with zero liquid discharge, and the evaporated water can be recovered. That can be used for purpose application like irrigation of agriculture field, and also importantly, the salts within the brine can be nicely separated into the components with high value. We are not there yet. All right. So far, nobody is able to separate the salt from the industrial brine into different components with high purity. But we are working very hard towards that. All right. This is pretty much the end of my talk today. I'm gonna skip the concluding remark, but I spent 2 slides introducing our journal ES&T. So this environmental science and technology journal has a long history. All right, it was first started in 1967. So it is now 56 years old. The current editor-in-chief is Professor Julie Zimmerman at Yale University. Now, I want to say our journal is highly respected in the general field of environmental research, and it is one of only 82 Nature Index journals. So if you care about making contribution to the Nature Index of your university, of your research institute, of your country, all right, you should consider submitting your best of your work to our journal. All right, with that, I would like to thank you for your attention.